Good morning. I'm going to time myself because I have no idea how long this talk goes for. But thank you for having me. Today, I thought it'd be worthwhile sharing a bit of information about some recent pen tests that we've been conducting and how AI is being incorporated in web applications. So I've been working in security for the last 10 or so years, predominantly as a pen tester, but have done several roles in a build capacity. I was an infrastructure engineer for a while, then a pen tester, then a security consultant, and then GRC, and that was a very short length of time, and then back into the engineering side. So I'm doing cloud security engineering at the moment, but still get my hands dirty with all the web app pen tests that come through. So today there's a couple of clients that I'd like to share. Apologies in advance that it's a little bit ambiguous, trying to keep some client confidentiality, but the two that I'll be speaking about are a federal government client and then a private software developer. So each of these clients engaged us to perform penetration testing, and so what drove them to do that is with the recent advent of AI becoming a lot more prevalent in the day-to-day life of most organizations. It's being integrated into all of your technologies. It's on all of your Apple devices. It's in all of your Microsoft devices. It's very difficult to not have an AI-enabled device. That risk management frameworks are now starting to be developed to support conscious decision-making around the introduction of AI and integrating and using AI. So a lot of the government agencies across Australia have developed their own internal policies and standards about responsible use of AI. There's whole of government advice from the DTA regarding the responsible use. There's EU's put out an AI Act. The US Department of State's also got an enterprise-level strategy. The NIST AI risk management framework as well is what a lot of these are modeled off, and within each of these frameworks and standards and policies there's a recommendation for proactive mitigation of potential risks and vulnerabilities within AI, but none of them say how. They don't advocate for penetration testing or any other type of technical assurance. They just say just go and check your risks. So there are a few technical frameworks that are out. Google have released some advice around being proactive and performing red team assessments against your AI infrastructure. Microsoft actually released a tool. There's a Python red team framework called Pirate, which assists in automating attacks against AI. And OWASP have always been at the forefront of web application security, and they've got their own recommendations around what are important risks within AI and large language models. So the first client that we did was about a year ago now. A large federal government agency operate a web-based service that incorporates AI. So this service is available to the public, so anyone can go and use this service, and it's about intellectual property rights and putting through logos and other imagery for comparison. So what can happen is if you're a user and you want to trademark something, you'd put forward an image or a phrase or a catchphrase or something like that. The AI comparison engine would then compare that against other imagery that may be publicly available, and then you get a response, which can either be favorable or unfavorable depending on how similar you are to previous submissions. So technically what that looked like, this is a very high-level diagram, but you have an uncontrolled endpoint, so a personal PC or some other type of submission endpoint, goes through the standard cloud infrastructure and edge security devices. There's WAFs in the way. There's other perimeter controls around the cloud instance that they were running. The web service is an Azure app that has modern frameworks that incorporate web application security. It then has the comparison engine. So that was a closed AI model that was developed internally, and was trained upon a proprietary data set that was then hosted on-prem. So that data set and the data warehousing was on-prem infrastructure and was used to then train that model. So one thing about these two clients is that they developed their own AI models for very specific use cases that they wanted to then offer as services. So neither of the assessments that we did used a natural language model or any of the publicly available AI that you can typically get. So after discussing this with the client, we developed a threat model and what are the potential risks that this AI would be exposed to. So we settled on attempting to poison the model with junk data, seeing as there was a user submission and file upload and there was a way to integrate with this model. We could potentially fuzz it, we could potentially try to retrain it through an exhaustive attack. Additionally, the output handling of whether or not the comparison was favorable or unfavorable, if we could manipulate that in such a way to get a favorable outcome for an unfavorable submission, then that's going to erode the integrity of the solution and there's a loss of trust then in the service. So what we did with the data and model poisoning, we generated an image. We submitted that as the baseline and then said we're going to start modifying this image. So it ended up going through, I think, about 1 million iterations as we slowly started to change both the data of the image as well as the visuals of the image. So I've got on the next slide what that kind of looks like. But after submitting 1 million or so images, we were trying to map out the bounds of what is considered similar or dissimilar. So those guardrails and those decisions weren't publicly available. And so as a user, when you're submitting your image or your catchphrase, there's nothing to say what is considered 30% different or 50% different or whatever that similarity rating that you get, what is that the metrics involved in that decision. So we set out to iteratively work through what those would be to then manipulate and determine the next output handling. So if we could say that a image is 31% different to a previous image, then we get a favorable outcome, and then we know that 29% different is going to be an unfavorable outcome, whether or not we can then manipulate that decision-making process to give us a more favorable outcome. One thing that we also identified was you could submit images and you could submit text, both individually. However, the model would identify text within the image. So there were different similarity decisions and controls for whether or not you submitted a file or whether or not you submitted text. So whether or not the controls on the text-based algorithm were replicated on the image is something that we set out to identify. So you could see there that we have text was identified in your logo. Did your image contain text? So whether or not we did yes or no would then determine whether or not that outcome was a more favorable outcome. So we went through a number of iterations of just pasting text in, adding actual text, doing image that looks like text. So instead of doing like ASCII characters, you do like a get paint and do some chicken scrawl, anything that could be considered text, but it was very good at picking all of that up. So what this kind of looked like was we started with an image, and so the difference between those two images visually is quite stark. We've got only 2 dots in the first one, 1 dot in the second. There's only half an image. Those two, from their data standpoint, are 99.99% similar. All that we did was, within just a hex editor, go through and started to swap bytes. So from the model's perspective, the two files that were submitted were very, very similar, but visually quite different. So I've highlighted there the Fs that we put through. That caused a malformed image and it didn't render the second half. So as a visual aid, you could say that we've potentially got a favorable outcome for only half an image, even though the data might be different. And we went through and did this a lot to try and manipulate what that model's decision-making process could be, or trick that algorithm into giving us a more favorable outcome. Additionally, we added in prompt injections. So if people are familiar with AI jailbreaks, it's where you put forward a set of instructions to an AI model to override the previous instructions. So generating what is considered protected content, things that might be sexual in nature or like malicious. If you ask ChatGPT how to build a bomb, it'll say this is outside of the safety instructions that I've been given, and there exists a family of attacks on AI prompt injection where you can override those previous instructions with specially crafted prompts. We also added a bunch of those in as either metadata or directly within the image to see whether or not we could override that algorithm within the comparison engine to say, just give us a favorable outcome for everything. So the results is we were unsuccessful on all fronts. So the data poisoning and the model manipulation, the controls that they had in place there, it was a completely closed model. The training data that they'd built this model on was closed source. There was no new information being accepted within the model. It wasn't doing any generative capabilities, and it was a very closed circuit within the algorithm. We robustly tested that, went through with all the different types of attacks that we could think of, and ultimately unsuccessful. Additionally, with most of the standard web application attacks that web applications will face, those were used again to validate whether or not the controls and the user input was going to be treated appropriately by that server and by the application that was making those comparisons. So the modern frameworks that they were using, the cloud-hosted infrastructure, the WAFs and the security devices, that defense in-depth approach was effective at identifying each of these fuzzing attacks, any types of data manipulations, and the prompt injection just fell completely flat. We have no evidence that it was even accepted or interpreted on the engine side. Because a lot of these models, once created and published, you don't see what goes on inside. They're much more of a black box. You can train it, you can get a clear outcome. So once you set the instructions, you treat it with a particular motivation in mind. Once it's trained and once it's giving you that baseline of functionality and you publish that model, it then becomes reasonably closed source. There is some algorithmic decision-making process that you can get into, but whether or not it determines exactly every step depends on how good you are at data engineering and reverse engineering in AI, but it's usually relatively black-boxed. So the second client was a lot more successful. It was a software developer and a service provider that would develop and have developed a web-based system engineering platform that's used for developing model-based technical diagrams. My systems engineering is quite poor, but there were it was a fully fledged application that was aimed to replace a lot of the thick client graphical diagrams. It built in a generative AI to assist engineers in building out these diagrams and filling in all the blanks. Having a complex digital system, it doesn't have to be a digital system, systems engineering is applicable to a whole range of complex systems. It doesn't have to be exclusively IT, but with these complex systems and all of the different data flows, inputs and outputs, and the relationships and dependencies between all of the parts, it's difficult to keep track of. So the solution that this software developer provided was a web-based platform with a generative AI that will help you track and manage all of those connections. One of the key features of this one is you could also export those systems and share them. So after spending a significant amount of time developing a systems engineering process and a complex diagram of what that system is, you can export it and then share it to either other clients of the platform or internally within your own organization. So this one was a little bit more complex than the first, and each client or customer of the software developer would have their own isolated cloud tenancy. So it would be accessed via a web browser. It was running on IaaS within the cloud, so the application itself wasn't making use of any of the microservices or app services that are native to cloud. The application was a thick client just hosted on IaaS. It also then had local databasing within that tenant as well. It had the AI, a copy of the AI engine specific to each client, local to those instances. So each of the clients, each of the customers of the client would have their own isolated instance. There was a security boundary around it, and that would be fed from that shared software developer environment. So patches would come through, updated reasoning and algorithms from the engine, because it was going to be continuously developed. There was also other shared services like account management and other logging if required, but they also had that project library. So when the systems engineering diagrams were created, exported, and then shared, there was a project library that was maintained by the developer as well. So after discussing what potential risks that they may face, we developed a threat model very similar to the first client. Any use of an AI model or engine is going to be vulnerable potentially to poisoning attacks. Additionally, given there was an export and sharing function of this client data, there was concerns about data exfiltration and whether it's sensitive information disclosures. As well, given the complexity of systems engineering processes, having an AI tool trained to provide recommendations, if those recommendations were wrong or if they were uninformed and that systems engineering diagram was then corrupted through poor validations, that could then have real-world knock-on effects, because these systems engineering processes do have real-world use in conducting business operations. So the way that we went to attack this one is that the model still had a training capability enabled. Given that it was a generative AI, it was designed to be contextual to the systems engineering process. So as the projects were being created and each of the components of that system were being developed and filled out, the AI would learn what was going on and provide recommendations. So if you have step 1, build a computer. Step 2, install the operating system. Step 3, install your apps. Then the next project that you create, if the first step was build a computer, then the AI would go, I've seen this before, let's install an operating system. And so what we went to do was build a whole range of projects with all the same steps and then add in malformed data. So using standard web application injection attacks, we added a whole range of payloads into each step with conditional triggers that if they were recommended in a future project, they would fire. We then added sensitive information and canaries across the platform so that the names of each of the dependencies, names of the components, the names of the data or the data flows, how they were being conducted, whatever content and artifacts were going to be contained within this diagram, we wanted to flag what ones are being redacted when shared and which ones make it through. So after putting through, I think it was 5 projects, each with a couple of hundred artifacts or objects within each, they were all tagged individually to ensure that anything that made it through, we would know on the other end. We then had output handling. If the recommendations that the AI were going to be providing were either malformed or a payload or some other type of malicious data, did it have any due diligence or output encoding or any security at all on whether or not this was going to be safe data for the end users to use? It was not. So plenty of alert boxes, prompts, other cross-site scripting. The recommendations that were being made would pull in data from remote sources as well. There was cross-domain protections not in place. There was a number of standard web application risks that were being introduced and propagated by this AI model. So on the right, you can see the test case. So this was one of the objects that were available to the systems engineers when they were developing their complex models and saying, what is the next step? Do we need any test cases? Are we doing UAT? Are we doing functional testings or security testings on each of the steps within the diagrams? And this also allows you to do custom icons. So when you have the high-level view of the diagram, step 1, you can put in an icon or a picture to represent what that is. So if you're going to build a computer, you can put in an image of a computer. That also didn't have any validation on it at all, and you could put your payloads within the images as the tagline of the images, the file names of the images. There was, for how large an application it was, the AI model that was providing these recommendations and consuming all of that data exponentially grew that attack surface. So the data poisoning, as you saw, was quite successful. We produced a repeatable pattern of development that was then learned and taken on by that model and then recommended at later stages during the application. Additionally, the edge security devices, so with a typical web application firewall and perimeter defenses, there was restrictions for the end user. So putting forward your script tags gets picked up by the WAF. However, if you build multiple processes through, you bypass that WAF, and that payload then gets accepted as a recommendation for the model, it would then use it throughout the rest of the application, and because it's an internal trusted source, it bypasses a lot of this edge security controls. Additionally, we had IP whitelisting and other allow lists for network access to these applications, which were not replicated on the internals. So the model could reach out to any of the untrusted domains and pull in that malicious, externally hosted malicious data. When we went to export our Trojan horse of a project, we pulled it out, shared it to a different tenant, like a different customer, and all of the fields that we originally tagged with our canaries were still present. The redaction of sensitive client information seemed to only target a couple of fields that the model thought were important, which was the content. So as we could see in the create new case there, having the content redacted still left a lot of the other test conditions. So relationships, dependencies, desired outcomes, the names were all still present. And so moving data from one model to, from one client to another client was then trivial. Added on to that, there was a significant amount of metadata on each of these projects. It gave us who each of the users were, who was a shared by, like original creators, modified. It also then included a whole bunch of cloud metadata. What infrastructure was being used? What were the unique identifiers for each of the components and the services within that cloud tenancy, which was all of the reconnaissance that a standard hacker would look to do right there in a nice JSON blob as the first thing in the project that you see. And then that output handling, there wasn't any. So that was one of the recommendations that we had to make. So out of both of those clients, the first one we barely identified any recommendations to make. It's hard being a pen tester and not finding anything. You write an empty report and you go, hey, good job. But the second one, we've been working with that client for the last sort of 9 months about secure development practices, ensuring that user input isn't trusted, as well as having outputting coding and doing safe recommendations. So the AI model has gone back, it's been retrained, it has consumed now a lot of payloads, so it has a rule set akin to a WAF where it'll identify script tags, it'll identify meta characters, and there are safe data types now that it will recommend. So there's a trusted list of objects, so as you create a test case, there'll be a dependency, there'll be another connection or a data flow coming from that, and that's now on an allow list of things it can recommend, as well as what data can be included in that. So it started off with a very complex application that missed all of the security tools, and now it's kind of that balance between the functionality and the security is now sort of being met. So integrating these AI models into web applications is happening more and more. We're seeing that across a lot of our pen tests that it's going beyond just having that natural language chatbot or having an AI agent or a help desk. There's now some legitimate use cases for AI. And things like this don't really get seen by the wider industry because they're proprietary data, they're the models that are being trained and developed then hidden behind commercial paywalls. And so it's very expensive to get access to a systems engineering platform that does your job for you. So these types of integrations, it's difficult to learn from other people's mistakes, and that's why I think it's important to talk about. But the approach that if there are pen testers here, if they do come across any of these AI integrations, a lot of the same tools. So we used Burp, we used command line, a lot of just the standard command line tools did all of the things that we needed to do, and it was much more about the process and the methodology that you look at attacking these kind of things. Integrating the OWASP, LLM, and AI security risks with those of the top 10 web application security risks. The crossover is almost one-to-one. They're very similar risks when you discuss the business impacts that exploitation may have. So it's been a pleasure to be up here and talk in front of you all. If there are any other questions or you'd like to discuss the methodologies that we did in any sort of further depth, please come and find me. But otherwise, thank you. Cheers.
You'll see I've been handing a brown paper bag to the speakers, and I promise it's not as dodgy as it seems.
That's disappointing.
All of the speakers that you're seeing today have spent a lot of time, right? It's not just the time up here on stage. They took the time to come up with an idea for a talk and submit it, and openly we can't accept everything anymore because we get more submissions than we can fit on stage. There's also a huge amount of prep that goes into, yeah, you did that work, but then you've actually got to put a slide deck together, have the confidence, I don't know what word you want to use, to get up on stage. So we're really appreciative, because obviously we wouldn't have a conference if we didn't have people on stage. It kind of doesn't work. So I did just want to highlight a few things. We've got a coffee cup, a CrikeyCon coffee cup, obviously, and coffee, which we can swap for tea. Kirstine, if you see her, has done some amazing artwork for each of the speakers that they will get to take home, as well as a challenge coin and a couple of stickers. And it's just our way of saying thank you. So Tim and the others that have come before, please make him feel really appreciated, because thanks.
Thank you. Cheers.